Welcome to the Explainer. Today, we're diving into a completely fascinating real-world Haskell refactoring journey by a developer named Ang. Now, if you've ever dealt with a messy code base where data is just kind of passed around blindly and you're constantly crossing your fingers hoping it's been checked for errors, yeah, you know exactly how stressful that is. Ang actually tackled this exact problem head-on, and the solution is something literally every software engineer can learn from. Which brings us to a pretty bold question. How do you actually guarantee that your code never runs on unvalidated input? This is the central conflict we all face, right? We build these pipelines, we write our functions, we accept external files, but once that data is inside the system, how does a function deep down in the architecture know, for an absolute fact, that the data is safe to use? Without a hard guarantee, it's just raw data floating around, crossing its fingers. And a system like that is inherently fragile. So today, we're going to solve this using a really powerful design philosophy. Let's get right into section 1, the problem with primitive data. Okay, so before this big refactor, Ang's codebase was, well, it was in a pretty precarious state. It relied entirely on a primitive, untyped data structure to pass things around, specifically a tuple made up of args and a lazy byte string. Now, we've all been there. On the surface, a tuple is super quick and easy to just throw together. It bundles the command line arguments and the file content perfectly fine. But architecturally, it is completely lacking in semantic meaning. It tells the next function absolutely nothing about the state or safety of the data inside it. And that is where the hidden danger lies. Because it was just a primitive tuple, that args record was being passed around completely blindly. There was literally zero guarantee that the file path inside had ever been checked. It was a totally fragile setup. Any calling code further down the pipeline was constantly at risk of processing unvalidated input simply because the tuple itself couldn't prove that a validation step had ever actually happened. Which brings us to section 2, parse, don't validate, a total paradigm shift. To fix these hidden vulnerabilities once and for all, Ang implemented this brilliant shift. The whole parse don't validate concept is beautifully simple in theory, but man, it is transformative in practice. Exactly as Ang puts it in the dev notes, it's the design pattern of moving away from primitive or untyped data and moving toward a strongly typed representation. So instead of just inspecting the data, shrugging, and passing that exact same primitive data along, you parse it into a brand new strict type. It's kind of like, instead of just checking someone's ID at every single door, you hand your functions a strict, unforgeable VIP pass at the entrance. If they don't have the pass, they don't get in. When you look at how this changes the pipeline, the function signatures are totally different. Instead of an old validate args function that just spits out that exact same primitive tuple we talked about, Ang created a new function called parse input, and this returns something called ValidInput, a brand new, highly specific entity. So it's no longer just a validation step that leaves you holding raw data. It's a parsing step that creates a concrete, tangible representation of safety. Moving into section 3, building typed representations. So what does this actually look like in the codebase? Well, you take that messy, primitive tuple of args and byte string, and you replace it with a clean, robust, new record type called ValidInput. It's no longer just two random pieces of data glued together. By giving the data a meaningful name, you immediately signal to any developer reading the code, and crucially to the compiler itself, what the exact verified status of this data actually is. Specifically, Ang wrote a ValidInput data type with two clearly defined fields, vargs for the arguments and vcontent for the byte string. It perfectly encapsulates the parsed arguments and the file content under one meaningful name. It actually holds the exact same fundamental information as the old tuple, but it wraps it up in a concrete identity, and that fundamentally changes how the rest of the application interacts with it. Now here is the absolutely crucial takeaway. It's this concept of the type acting as proof. I know that sounds a bit dense, but it is vital, because the only way to construct this ValidInput record is by passing data through that parse input function. Simply holding a ValidInput value acts as absolute proof of three things. First, the input file definitely exists. Second, it is for sure a text file. And third, the content is valid UTF-8. You don't have to guess if someone remembered to do those checks. The type itself is the mathematical receipt that they were done. And that drives home the biggest security and stability benefit of this whole refactor. Once you change your downstream functions to require that valid input parameter instead of a generic tuple, your calling code is mathematically guaranteed to never process unchecked data. It's literally impossible for an unvalidated argument to slip through because the compiler simply will not accept it. You've eliminated an entire class of runtime errors just by designing your types correctly from the start.
Finally, Section 4, the extensibility payoff.
Now, doing this kind of deep refactoring definitely takes time. In fact, Eng noted that it took quite some moons to finish. But to really see the real-world payoff here, listen to Eng's exact realization at the end of the process. They said, if I later need to add a third piece of metadata during command line parsing, I can just add a field to ValidInput without breaking existing code. I mean, that is just music to any developer's ears, right? Adding future metadata is suddenly trivial instead of turning into a massive architectural headache. Just think about the downstream impact for a second. If you wanted to add a new field using the old primitive tuple, you would have to track down and modify that tuple everywhere it appeared in your codebase. It would create catastrophic breaking changes across the whole application. But with the new ValidInput record type, you literally just add a field to the record definition. It integrates seamlessly. The compiler guides you, and your downstream code remains totally untouched and perfectly stable. By adopting this parse don't validate pattern, Eng didn't just patch a small bug. They fundamentally upgraded the safety, the clarity, and the future-proof nature of their entire Haskell project, which leaves us with one final, pretty provocative question for you to think about. What primitive data is hiding in your codebase right now? Where are you just validating when you really should be parsing? I challenge you to take a look at your own code this week, find those hidden tuples, and apply this exact philosophy to build something truly robust. Thanks for joining me for this explainer, and happy coding.